Okay, last class we read about the solubility. With respect to that, we read about a law, that is Henry's law, which is talking about your solubility of gas in the specific solid, right? So solid or liquid, it depends on that medium, but mainly I'm talking about the gas in solid. And in that case, we read about how the partial pressure is directly proportional to the mole fraction, right? Now the next thing what we're gonna read about, that is vapor pressure. This topic, which is again connected to one more law, which is just an application of your Henry's law. So you may find there are certain similarity in this law with the Henry's law, and there is only the minute difference, that is the solvent which you are taking, and as well as the reactivity of the respective solute in that solvent. Okay, before that, before going to that factor, let's start with the simple thing, that is what is vapor pressure. As if you define in the most simplest way, vapor pressure is just a pressure exerted by the vapors. That is a simple thing जो कोई भी बता सकता है, that it is the pressure exerted by the vapors. Now, where they will exert, that is a question. So obviously I'm talking about vapor pressure of liquid solution. So liquid solution, what does that mean? We read in the previous topics that liquid solution means where solvent will be fixed as liquid. So vapor pressure is simply, with respect to the liquid solution, is defined as the pressure exerted by the vapors in the equilibrium with the liquid solution at a particular temperature. Now what is this definition means? अगर मैं एक solvent liquid ले रही हूँ और मैं उसी में जो solute है, it can be a solid, it can be a liquid, it can be a gas. But since I'm talking about vapor pressure, I'm saying that if solid if I'm taking, right, or a liquid I'm taking, then in that case, when you are mixing it with a solvent, and at that time if you slightly increase a temperature and you fix that temperature, तो obviously vapors निकलेंगे उसके, right, and वो जो vapors निकल रहे हैं वो vapors उसी within the vessel के अंदर निकलेगा, और वो vapors अपने आसपास एक दूसरे टकरा के उनका अपना एक pressure exert होगा, राइट. तो ये जो प्रेशर एक्सर्ट हो रहा है वो किस पे हो रहा है? उस लिक्विड सॉल्यूशन पे हो रहा है जहां पे ये वेपर्स प्रोड्यूस हो रहे हैं. सो दैट्स व्हाई वो जो प्रेशर प्रोड्यूस हो रहा है बाय द वेपर्स इन दैट लिक्विड सॉल्यूशन, दैट इज नोन एज वेपर प्रेशर, right? So in other terms, you can understand that vapor pressure is directly proportional to escaping tendency of that vapors. Okay, so vapor pressure is proportional to that escaping tendency. That's what I told you, right? So what does that mean? So the more the number of vapors will start going out of that solution, but within that vessel, that will obviously increase the pressure on the liquid solution. So that is the meaning of vapor pressure, directly proportional to escaping tendencies of the vapors in that solution, right? Now this is the simple way to explain what is vapor pressure with respect to this liquid solution. Now the question arises is, if the solute is a reactive one or maybe a non-reactive one, then what will happen to this vapor pressure and how it will get affected? So that is why we have two criteria, that if the solute is a non-volatile. Now what is the meaning of non-volatile and volatile? That is about the reactivity. More a substance is reactive. For example, I say that sodium is a volatile substance. So what is the meaning? The once you keep the sodium out in the air, it will immediately catch fire, right? So that is the immediate response or the spontaneity of that respective substance. So that is, you call it as a volatility. So if I'm taking a solute which is a non-volatile, it means, and it can be a solid or it can be liquid. So what will happen in that time? नॉन वॉलेटाइल का मतलब है अगर वो रिएक्ट ही नहीं कर रहा, देन उसका खुद का जो वेपर प्रेशर है, दैट यू कॉल इट एज पार्शियल वेपर प्रेशर, विल नॉट बी प्रेजेंट इन इट. दैट्स व्हाई उस तरीके के सॉल्यूशन में वेपर प्रेशर विल बी कैलकुलेटेड एज इक्वल टू द पार्शियल वेपर प्रेशर ऑफ द सॉल्वेंट इन द सॉल्यूशन. यानी कि वेपर प्रेशर हम निकाल सकते हैं जस्ट बाय गेटिंग द वैल्यू ऑफ पार्शियल प्रेशर ऑफ द रेस्पेक्टिव सॉल्वेंट विच इज अ लिक्विड, राइट? बट सेकेंड केस इज if the solute is a volatile solid or a liquid, that is the reactive one, in that case what will happen, तब हम वेपर प्रेशर जब हमें निकालना है टोटल, तब हम क्या करेंगे, उस सोल्यूट का वेपर प्रेशर दैट इज पार्शियल वेपर प्रेशर और सॉल्वेंट का पार्शियल वेपर प्रेशर, दोनों को अगर हम ऐड करेंगे तो वी विल गेट द टोटल वेपर प्रेशर ऑफ दैट लिक्विड सॉल्यूशन, right? So that's why vapor pressure of liquid solution cannot be calculated just by saying that it is the pressure exerted by defining a term. It's maximally depends on what type of solute you are taking, how much it is reactive in that solution. That will give you the value of that vapor pressure with respect to that solution. Now next is we are going to the next term, that is if we want to calculate vapor pressure, then we can find two specific properties, that if I take liquid in liquid and a solid in liquid, then what will be the effect on vapor pressure. So in the first case I am taking vapor pressure of liquid in liquid. So what is that liquid in liquid? It means solute is liquid and solvent is liquid, and I am giving you a condition that both are volatile in nature. What does that mean? If I am taking a vessel, I am taking both the liquids and they are volatile, then they will start evaporating immediately. So they will evaporate within the vessel in such a way that they will attain some equilibrium within each other. Now what is that equilibrium? If we are taking such kind of vessel where the escaping tendency is such that the evaporation is somewhere happening within the vessel, then in that case whatever is getting evaporated will get mixed with the another component in that solution. So in that case how we will calculate, that is I am considering 1 and 2 are the two components, P1 P2 are the partial vapor pressure of that two components or the two solute, and P total I am taking as the total vapor pressure, and I am considering x1 x2 which we have read already, that is called mole fraction. So x1 is for the mole fraction of the first component, x2 is the mole fraction of the second component. So by considering these conditions, Marty-Ralt in 1886 he gave one law which is just to explain that what is the relationship between this partial vapor pressure and the mole fraction with respect to the specific condition, that is liquid in liquid for a volatile nature, right? So Marty-Ralt, what he stated, that Ralph's law, that Marty-Law stated a law that is known as Ralph's law, which explained that in a solution of volatile liquid, this is the condition and this is the difference between Henry's law and Ralph's law. Okay, so that in a solution of volatile liquid, that is this condition is obviously most important and a difference between Henry's law and Ralph's law. So that is the partial vapor pressure of each component is directly proportional to its mole fraction. So this term we have read there, but what is the difference? We are talking about there the solubility of gas in the solid. That is the difference. Rest the expression is the same one. So that I can denote, for example, if I am talking about the first component, then it will be P1. P1 will be the partial vapor pressure of that first component. So that is proportional to its mole fraction according to the Ralph's law. So if I remove that proportionality, then I am bringing a term that is P1 naught. Naught is telling you that I have taken the pure component of that first component. What is that meaning? That partial pressure of the first component is P1, but this P1 naught is stating that the vapor pressure of the component in the pure state. That is the another way we can say pure component. So multiplied by x1. In the same way I have written for P2, that will be P2 naught x2, right? And we have read in the states of matter in the class 11 that according to Dalton's law of partial pressure, P total is the sum of the partial pressure of the individual gases. So P1 plus P2, substitute the value which we got from the first and second, and we will be writing as P1 naught x1 plus P2 naught x2. So as we also know, the total moles which is present in any of the reaction or the stoichiometry will give it as a constant as 1. That is the condition. The overall moles will remain constant. So if I want a value of x1, then what I can do? 1 minus x2. I can also calculate x2 value from this and substitute the value. You can do in either way, right? I have substituted x1 value. So I am substituting this in the expression third. So you will get some expression like this. P total equals to P1 naught plus x2 bracket P2 naught minus P1 naught, right? So this is that expression which is stating you about the total pressure of the solution with respect to the mole fraction, and you can see from the expression that only one component will be calculated in the form of mole fraction to get P total, right? So that's why you got to know that P total is actually proportional to the mole fraction of any one of the component. So if I plot a graph between partial pressure, that is the partial vapor pressure, and the mole fraction of the solvent, and since I have taken here both are volatile liquid, so obviously the total thing will be considered. So in that case you are having the solute factor, so that you will get a straight line, so it will sharply increase, right? So that is P total, that is the total vapor pressure, may increase or decrease depending on the P1 naught, that is the vapor pressure of the component in the pure state and in the second component as well, and with an increase in the mole fraction of the first component. So basically you can get the P total depending on the value of the pure components in their original state, right? Now this graph which I have plotted, this is very important and will be asked in the examination, but before that you need to apply all the concepts which you have listened right now onto this graph. So what I have done, I have plotted with respect to x1 mole as well as x2 mole in both the sides. I have taken on the x side vapor pressure, and on the this thing, that is the coordination, you can change in any way, but I have taken on the y-axis as the vapor pressure and the x-axis I have taken as the mole fraction. And what you can see at the down, you can see there is written x1 equal to 1 and x2 equal to 0. What is the concept? If x1 plus x2 equal to 1, I can keep any one as 1 to get the value equal to 1, right? So I have placed x1 as 1 and x2 as 0, and on the side I have placed x1 equal to 0, x2 equal to 1. This is just a combination graph. If I want to plot an individual graph, you will understand about how it is coming straightly. So if I go for x1, what you can see, 1 to 0. So obviously I have to go to the other side to get the straight line graph with respect to the first component. So from 0 it is increasing till 1. So in that case what will happen, if you are taking x1 as 0 and x1 as 1, it means it will show a graph from this side, straight line graph from the right hand side. So that value on the x-axis will be P1 naught, right? Now next what I have taken, x2 as 0. So it will sharply increase till x2 equal to 1. So on the right hand side the maximum will go to P2 naught. You may ask me why P1 naught on the bottom side and P2 naught on the higher side. So the condition what I have taken is, if in case both are volatile, that we know, but if in case sometime the reactivity may change during the reaction, at that time if one of the component found to be a little bit volatile as compared to the other one, then in that case the vapor pressure of that component will be less than the other one. That is the reason here I am considering first one is less volatile. So automatically I have told you that the volatility is directly proportional with respect to the vapor pressure, right? So that's why P1 naught is less than P2 naught. So that's why P1 naught on the little bottom side and P2 naught on the higher side. And if you count P1 naught plus P2 naught, what will you get? P total. That's why the total partial pressure can be P1 and P2. So PT equal to P1 plus P2 on the upper side, and if you join it you get a straight line. Now this side it is going P1, that side it is going P2, and that is the reason they have been marked like this. So from this combination reaction you can understand how the partial vapor pressure is correlated with the mole fraction and how the volatility is affecting the overall vapor pressure of that liquid solution. Okay, So we have read about that is the vapor pressure with respect to the volatile solution, right? Now, if we want to calculate the mole fraction with respect to only in the vapor phase, then how do you do? We have done this expression, that is Pi equal to Xi or Yi into multiplied by the total pressure. This we have done in the Dalton's law of partial pressure or the Dalton's law of pressure in the class 11. This expression we can use it for numerical purposes, right? So this Pi, that is the partial vapor pressure of that liquid, of the individual liquid, that is equals to the mole fraction of the respective liquid multiplied by the total pressure will give you the individual partial vapor pressure with respect to the total pressure. So this expression we can use it for calculating with respect to total pressure. Now next is vapor pressure of solid in liquids. Earlier we read about vapor pressure of liquid in liquid and considering the case that both were volatile. Now is the case of non-volatile solute. So what will happen? If I am adding a non-volatile solute, that is which is not reactive in nature, then what will happen? It will in any way, if it is a soluble or if it is an insoluble, it will suppress the solvent which is present in the solution. That is, if a non-volatile solute is added to a solvent, the number of solvent molecules escaping from the solution will get reduced. Hope this is very easy to understand that अगर हम ग्लूकोज को मिलाए या यूरिया किसी भी चीज़ को मिलाए, सॉल्ट को मिलाए, किसी भी ऐसी चीज़ को मिलाए जो सॉल्युबल है या इनसॉल्युबल है, वो कहीं ना कहीं जो सॉल्वेंट की जो जगह है या तो पूरा ले लेगी या तो उसकी जगह को ऑक्यूपाई कर देगी, जिसकी वजह से सॉल्वेंट का उस सॉल्यूशन से बाहर निकलना मुश्किल हो जाएगा. तो उस टाइम पे क्या होगा? उस टाइम पे अगर आप देखोगे वेपर प्रेशर अगर विद रिस्पेक्ट टू सॉल्वेंट अगर आप देखोगे तब उसकी वेपर प्रेशर कम हो जाएगा. और मैंने अभी पहले बताया था कि अगर नॉन वोलेटाइल प्रेजेंट है तब हम जो पार्शियल वेपर प्रेशर निकाल रहे हैं दैट इज ओनली विद रिस्पेक्ट टू द सॉल्वेंट एंड नॉट द सोल्यूट, बट दैट वेपर प्रेशर विल गेट रिड्यूस. Why? Because of this reason. So that is, if I am considering P1 as the vapor pressure of the solvent and X1 as the mole fraction, then P1 is equals to P1 not X1. Again I am applying Rolle's law, and which is again is equal to P total. Why? Because only solvent molecule will give you the value for P total. So if I plot the graph in the same way I plotted for the volatile one, you will see a sharp increase or a linearity that is showing you that it is increasing, but this vapor pressure, if I go with respect to the vapor pressure increasing from this side, then if I go from 1 to 0, then overall that vapor pressure will show a sharp decrease, right? Now after vapor pressure of solid and liquid, there are certain conditions which are an application of the Rolle's law, that is an ideal solution and a non-ideal solution. So ideal means a solution which is perfect. Now what is perfect? A solution which is somewhere connecting with the Rolle's law conditions that will show ideal solution. So that is the definition, that is the solution which is obeying Rolle's law under all condition of the temperature and concentration, whether it is a dilute or whether it is a concentrated. If it is going with that and obeying that condition of Rolle's law, then it will be called as ideal solution. So the condition for this is that delta H mixing is 0, delta V mixing is 0, and the attractive forces are almost equal. Now what I said, I'll explain that if I'm taking two components, a binary solution, in that there are A and B. I'm considering that A is the solvent and B is the solute. So if you mix those compounds which have the similar property or the like solvent or the like substances, for example, I am taking benzene and toluene. They both come under polar solvents or not exactly the polar, but they have the maximum property of non-polarity. But until they mix with some compounds which are reactive, then they come under the polar compounds. Right? So if I mix benzene and toluene, they belong to the like factor, the similar factor. So in that case, there will not be any change in the interaction between benzene and toluene, benzene and toluene. What I want to say is, if two different things are combining or if two same thing are combining on itself, then the overall attractive force will always remain the same. That is the basic condition of ideal solution. So that's why the examples are benzene, toluene, hexane and heptane. They come under hydrocarbons, right? So you can take n number of examples just to concentrate on the factor of ideal solution based on this concept that the overall interaction between two different compounds and within the compounds will show a similar force of attraction. Now next is non-ideal solution. By the term non-ideal means which is somewhere not perfect or with respect to the Rawls law. That is, which does not obey Rawls law. Those solutions will come under non-ideal, and the condition is over entire range of concentration. You cannot write that those does not obey Rawls law is non-ideal. You cannot say like that. It has to be explained with respect to the concentration. So that's why these definitions are to be written with respect to concentration. Now, in non-ideal solution, you have certain things that sometimes the attractive force may be higher between two components. Sometimes within the component the attractive forces may be similar. So in that case, there will be arising two deviation. One is positive deviation, another one is negative deviation. And today just explaining about the positive deviation. That positive deviation, here the force of attraction between two different components or the compounds will be less than the force of attraction within the components. For example, if I take alcohol and acetone, everybody remembers alcohol has highly reactive or highly electronegative oxygen atom and as well as hydrogen atom. And you know the basic condition of hydrogen bonding. So alcohol has hydrogen bonding in it, and this hydrogen bonding gets breaked up in the presence of acetone, because acetone molecule will come in between this hydrogen bonding of alcohol. Therefore, what will happen? That within the interaction between alcohol and acetone, the intermolecular force of attraction which has got generated will be lesser. Why? Because hydrogen bonding has got disturbed and the alcohol molecules will start going out of that due to the intervention of this acetone, right? तो अगर अल्कोहल मॉलिक्यूल का हाइड्रोजन बॉन्डिंग इस एसीटोन के प्रेजेंस में डिस्टर्ब हो जाता है तो ओवरऑल क्या होगा, इसके एस्केपिंग टेंडेंसी बढ़ के इसका वेपर प्रेशर ज़्यादा हो जाएगा, राइट? जबकि अल्कोहल और अल्कोहल के बीच में हाइड्रोजन बॉन्डिंग इंटैक्ट रहेगा और एसीटोन के बीच में जो मिनिमम बॉन्डिंग है, that is a kind of hydrogen bonding, that will get similar. That's why A interaction or B interaction, that is same interaction, will be higher than the A and B, that is the solute and the solvent. Other example I have taken is carbon disulfide and acetone. So the concept is the same, that is the vapor pressure will get higher due to the less interaction between two different components, right? So hope everybody understood what is positive deviation, vapor pressure, what is the difference between non-volatile solute and volatile solute, how the terms gets changed due to the presence of two different components. Kindly read whatever I've explained. You can go through NCERT as well, and do let me know any problem if you're having. Okay, I will continue with the next negative deviation in the next class. Thank you.